1992 to 2003. And finally, he moved to KIAS at 2003. So for a long time, he has been working very actively in cosmology, and especially he did very great work recently, and he will talk about it today. So the title of this work is Discordance of Flat Lambda CDM Concordance Model, Evidence for the Dark Energy Equation of State Parameter, W is larger than -1. So, Professor, please.
Thank you very much for introduction. Good afternoon. I'm Changbom from KIAS. Today, I'd like to talk about one of my recent works for measuring expansion history of the universe and also dark energy equation of state parameter W. So this work has been done for many years now. The recent paper was mostly written by Fuyu, who is now in Winnan University. But there are many people who has joined in this project. So how can I? This one? No. This one doesn't work somehow. It works. Okay, so all this project has been motivated by Bohdan Paczyński long time ago. So let me briefly talk about my personal story with him. So it was November 1990. I visited Princeton University, and one day he came to me and asked me to have lunch with him. So on that day, he came with a sheet of paper, which was just one-page Nature paper, which is shown here. So he told me that the paper has a wonderful idea that allows us to measure whether or not cosmological constant is finite. But he said nobody was working on it after more than 10 years after the paper was published. So he recommended me to work on the idea. But at that time, I was busy doing other things. So even though I promised him to work on it, it was only in 2005, 15 years later, when I really started to work on it. And after 2008, I had a postdoc who started to work on this, and that was really the beginning of this project. So over the past about 15 years, there were many efforts of ours to elaborate this method and apply the method to observational data to get constraint on cosmological constant. So let me very briefly explain what the idea is. So we basically use something called standard shape. So we use the shape of the cosmological object to measure the expansion history of the universe. So for example, look at these two density maps. So on the left, you are looking at the initial density field at z equal infinity. And then we make an embodied simulation to move matter particles to the present epoch, z equals 0. And on the right, I'm also showing the density field smoothed over 25 megaparsec. And you can see, even though there is huge nonlinear evolution on small scale, on large scale, the general shape of density field hasn't changed much. So there is conservation of the shape of large scale structure on large scale. So this is something we can use to measure the cosmological parameters. So later I'll explain how this shape or pattern in the large scale structure can be used to constrain expansion history. And this is called standard shape because this is more or less very insensitive or independent of evolution. And also, if you compare the distribution of matter in 3 different cosmological models with very different shape of power spectrum, for example, on the right, you have a cosmological model that has flat power spectrum, which I call white noise. And the second one is standard CDM. This is a very long time ago. And on the right, I have hard dark matter power spectrum, which has a strong cutoff on small scales. So even though the shape of power spectrum is very different, you can see the overall the pattern of large scale structure are the same. So this method, if you use only the shape, geometrical properties of large scale structure, this method is more or less independent of the shape of power spectrum and the amplitude of power spectrum as well. Okay, so that's very brief summary of the idea. So let me go to this page, which has a few formulae summarizing what the test is. So look at the rightmost part, this one. Okay. So suppose we have an object like supercluster or some distribution of galaxies. In this case, I'm assuming it's kind of the object that is spherical, but it doesn't matter whether it's spherical or not. So suppose its actual size along the line of sight is delta R parallel, okay? And the size across the line of sight is R perpendicular. So that's the real size of that object sitting at redshift Z, okay? But the observational quantity we measure is not actual distance, but the redshifts and angular size. So on the right, I'm drawing the same object with observational quantities. So the line of sight distance, size, delta R parallel, will be observed as delta Z. And the size across the line of sight, delta R perpendicular, will be observed as delta theta, angular size. And the relation between delta Z and delta theta with R parallel and R perpendicular is given by these 2 equations. So these 2 are directly related, proportional, but there are quantities that changes the co-moving size for given observational quantities. And in the case of R parallel, there is 1 over H vector, the Hubble parameter is there. And in the case of R perpendicular, there is angular diameter distance and proportional to delta theta. And angular diameter distance is basically the integral of Hubble parameter. And the Hubble parameter is determined by expansion of the universe. And in the case of flat universe, so note that there's no curvature term in the middle. There is a matter density term here and dark energy term here. Okay, so in this case, we adopt dark energy model. So depending on what these parameters are, H can change and dA can change, and also that change the relation between observational quantities with co-moving sizes. So if you go out and observe a certain object for which you know the absolute size, then you can measure Hubble parameter and angular diameter distance directly from observational quantities like delta Z or delta theta. But suppose you don't know the absolute size, but you only know shape. I mean, the ratio between the size along the line of sight and size across the line of sight. Okay, so in this case, this ratio, if you take this ratio, then you get this ratio is proportional to 1 over dA times Hz, okay, apart from observational quantities. And again, if you know the shape, if you know this ratio, then you can measure this product of angular diameter distance and Hubble parameter. And if you find some object whose shape doesn't evolve, then you can constrain this product and also the cosmological constant which determines this product. So if you choose a wrong cosmology, suppose you chose, there are cosmological parameters which affect the expansion history, like omega matter, and in this case, omega matter and W as a function of time. So they will affect the expansion history, and therefore they will affect H and dA. So if you happen to choose wrong cosmology, wrong omega matter and W, then your conversion from redshift to homologic distance will be wrong. And that will give you incorrect product of dA and H. And you will see apparent evolution of shape. Okay? So this ratio will appear to evolve because you chose wrong cosmological parameters. So in this way, you can put constraints on these cosmological parameters by comparing this ratio at various redshifts. So this is the key idea of Alcock-Paczynski test. Okay. So in this case, you have to know the shape. You have to know the ratio between the size of the object along and across the line of sight. And if there is a spherical object or circular object, this ratio should be 1 at all redshifts. We are using a little different method. It's very almost basically the same as this, but we use an object for which we know this absolute size. The shape does not evolve. So we don't need to know the shape. We don't need to know this ratio, but we know this ratio doesn't change. So you may wonder if there is any difference between these two methods, but this method is more powerful because we don't rely on any theory. Okay, So as I wrote at the bottom, I'd like to emphasize we don't use absolute size, so we don't need to know delta R parallel or delta R perpendicular, and also the shape is not used. So we don't need to know this ratio, the value of this ratio. We only require the object we are using to keep their ratio at different redshifts. So that's the Alcock-Paczynski test we use. Yes. Yeah. We assume this ratio is constant, independent of redshift. Main assumption is that the object we are looking at is not changing shape. In other words, this ratio is conserved. So that's the standard shape we are talking about. So yeah, the name of standard is attached because this object is maintaining its shape. Okay? And that is why I'm showing this. Okay, you see, this is between redshift infinity and redshift 0. And you see on large scale, the general distribution of matter is conserved. So this is basically standard shape. That's the key idea. Okay, let me demonstrate you how this shape can be used to constrain cosmological models. So on the left, I'm considering 4 different cosmological parameters we adopt when the true cosmology is given by this. So suppose we live in a universe which is flat, geometrically flat, but omega matter is 0.26 and omega lambda. So we assume dark energy is cosmological constant in this case, and therefore W equal -1. So in this universe, we are observing galaxies at the vertices of these blue scales. So I have 3 scales here, and there are 4 galaxies at the corner. And now they will be observed by you by angle and redshift, right? So you have redshift of these 4 galaxies, and then you adopt cosmology to convert this redshift to co-moving distance. But now you don't know the true cosmological parameters. So you adopt a certain cosmological parameter to convert redshift to co-moving distance. And suppose you made a mistake in omega matter. Okay. So in this case, W is correctly chosen to -1, but omega matter is overestimated. So the true value is 0.26, but you happen to choose 0.4. So by choosing 0.4, you think universe is expanding slower than what the universe actually does. And in that case, your co-moving distance is underestimated, and these 4 galaxies at the corner of this scale will appear at the corner of this red scale. Okay? So they appear to be closer, but also distorted. It's a little bit squashed. If you choose too small omega matter, then universe is thought to be expanding faster. So the distance increases, and these 4 galaxies will be located in newer figure at further distance, but also is slightly stretched. So this case is this. So this is the product of dA times H, which determines the shape of your object. So I'm showing the stretch factor basically. So if you underestimate omega matter, the stretch factor is larger than 1. So as you go to higher and higher redshift, the stretch factor becomes bigger and bigger. So the object you're looking at will be stretched along the line of sight more and more as you go to higher redshift. But if you choose omega matter to 0.4, overestimate, then there is a compression, and this black solid line is the ratio between along and across the line of sight. Okay, so in this way, you realize your choice of cosmological parameters is wrong. So you search for parameter space until you find a set of cosmological parameters which makes this ratio independent of redshift. So that's the graphical explanation of this method. Do you have any question so far? Yes, Rodriguez. Right. So at the moment, I'm assuming there is something that maintains the shape. Okay. So regardless of what you are looking at, I'm assuming this object is keeping its shape. Okay. So in this case, if you choose the wrong cosmology, you can immediately notice you are making mistake because the shape is appear to evolve. Okay. So yeah, the next question is what kind of object can be really maintaining its shape? Okay. So as I showed in the beginning, the shape of logical structure is the one we are using, but this shape of logical structure, the observed shape of logical structure is distorted along the line of sight because of the peculiar motions. Yes. But I'll get to that later. That's the minor detail, but that minor detail has been the main problem with Alcock-Paczynski test for a long time. Yes. So that's the one one has to overcome. So there have been many suggestions recommending people to use different shapes, standard shapes, and also there is a standard population method as well. So this is basically the summary of all the method using Alcock-Paczynski test. So the original paper by Alcock and Paczyński, they suggested to use some spherical object, and supercluster was the one they mentioned. They just suggested the method, but they never went through the details. In 1994, that was 4 years after Bodan recommended me to work on it. So apparently, people start to pay attention to this method a few years later. There are people who want to use the pair of galaxies or pair of clusters, pair of quasars, and the angle between line of sight and the galaxy pair should be randomly oriented. So if there is anything wrong with the cosmology, then this random orientation will be broken, and that's the way one can constrain cosmology. The cosmic void should be spherical, okay, on average, if you take average over many voids. But again, if you make a mistake in the conversion from redshift to conmoving distance, the shape of this void will be either stretched or compressed. So that's Barbara Ryden's idea in 1995, and there are many people still working on it. And in 1996, there are two groups of people who suggested to use 2-point functions. And Bollinger, they proposed to use power spectrum of galaxies. And Matsubara and Suto, they suggested to use correlation function, 2-point correlation function of galaxies. And there are many more. So in our case, we use normalized 2-point correlation function in Redshift-space as standard shape. I'll show you how good the standard shape is, but it's pretty good. So we don't correct for the peculiar velocity effect, the Redshift-space distortion effect. We use Redshift-space distorted correlation function as the standard standard shape. Okay. Okay, so this is the concept diagram of this method. And on the left, you have a catalog of galaxies, which gives you angular position and redshift. Okay, so you have RA and DAG and redshift. Then you adopt a cosmology to convert redshift to comoving distance. And now you have a comoving distance and angular position. And that will allow you to make a map like this, the three-dimensional map like this. And then you divide this sample into a few different redshift bins and calculate the correlation function in each redshift bin. So you have a series of correlation functions at different redshifts and then compare, then normalize it, okay? And look at only the shape of this correlation function along and across a line of sight. And if you find, suppose this normalized correlation function is really not evolving at all in redshift space, then you can constrain cosmological models. You adopt it at this step by requiring this series of correlation functions at different redshift bins to be constant. So if not, you go to this step again and change your cosmology and do the procedure again until you reach a set of cosmological parameters that allow you to conserve the shape of correlation function. So remember, I'm using only the shape of the two-point correlation function in redshift space. This is purely geometrical and independent of size and mass and clustering evolution, because I'm normalizing the amplitude of correlation function. So to linear order, even if there is a growth of clustering, it doesn't affect this method. Even if there is a size growth, it also doesn't affect the result. Okay, so here is some numerical calculation using cosmological simulation. So first look at these four figures in gray, and they are two-dimensional correlation function along and across the line of sight. I mean, if you have a distribution of galaxies, you look at one galaxy, you visit one galaxy and look around all the galaxies nearby and calculate the correlation function along and across the line of sight separately. And that's the numerical result here at different redshifts. So from redshift 0 to redshift 1, at the moment, we really don't go to this far. We go out to about redshift 0.6 at the current data. The dash data will allow us to go to about 0.9 or 0.95. So we are basically living in this redshift range. And you see, well, at the bottom, the color plot is the difference between these correlation functions. So, for example, this one is the difference between g equals 0 and g equals 0.15. And this is 0 to 0.5 and 0 to 1. So this one. And if you look at the amplitude of this correlation function, you can see the amplitude is of order of 1 here, the correlation function amplitude. There is, but the difference between this redshift space correlation function at different epoch between g equals 0 and at other epochs is of order of 0.01. So the redshift space distortion makes the correlation function greatly distorted, like what you see in this gray plot, okay? But the evolution of redshift space distortion, distorted correlation function is 100 times smaller. So there is evolution. There is a weak evolution, which we should correct. But this redshift-space correlation function is quite good standard shape to this sense. Does it answer to your question? Okay. Okay. So we choose redshift-space correlation function, the shape of the redshift correlation function as a standard shape. And this is actually normalized by this. So we integrate correlation function over some separation and then divide the correlation function by the integral of this correlation function, which is shown here. Okay. And then we worry about this small evolution. Okay. So even though we find this redshift-space two-point correlation function is a very good conserved statistics, they do evolve. So there is a systematic evolution, which we should take into account. So we make a series of embodied simulation to estimate this small systematic evolution. So we basically made 10 cosmological simulations with different omega matter and W. So the central model is this one, which is WMAP 5-year cosmology. And then we vary omega matter and also we vary W. So in each model, we estimate this small redshift evolution of redshift-space two-point correlation function, and then use that to make a correction. Okay. Well, this basically shows how this redshift-space two-point correlation function evolves and also depends on different cosmological parameters. So we went through all these cosmological parameter space and measured the cosmology dependence of this evolution of shape of correlation function. Now we are ready to apply our method to the observational data. And so this work was done before DESI. So we are currently working on DESI data. And hopefully at the end of this year, we can come up with a new result. But for now, we use only Sloan data. Okay, so Sloan data is already quite good enough to put very interesting constraint on cosmological parameters. So we divide these 4 data into 7 redshift bins. So the lowest redshift bin is given by the original Sloan 1+2 survey, DR7. And then BOSS survey gives us low-Z and CMAS. And low-Z is divided into 2 bins, and CMAS is divided into 3 bins. And EBOS gives us the additional bin at high redshift. And in each redshift, we calculate two-point correlation function, which is shown here. So these 7 panels, except the last one, are showing the correlation function of observed galaxies. The color contours are the two-point correlation function of observed the SDSS galaxies in 7 different redshift bins. If I stack all of these correlation functions, and that is shown in the last panel. And in this calculation, I assume these cosmological parameters, the omega matter 0.26 and W equal -1. So I assume this model to convert Sloan redshift to co-moving distance and then calculate two-point functions. And I find the shape of correlation function is already quite constant of redshift. Okay, so they all overlap to each other. So this cosmology is already quite close to the truth. And that's why this has been standard model for a long time. But we have a better constraint of this, which I'll show you later. And the gray lines are the correlation function from Mach surveys in our cosmological simulations. And you see these cosmological simulations can reproduce the shape of correlation function very well. And these cosmological simulations are basically used to estimate any kind of systematic bias, which is shown here. And also that is used to estimate the error bar. So look at this parameter space. This is dark energy equation of state, the y-axis, and the x-axis is the density parameter. And I assume flat universe. So omega dark matter is 1 minus omega matter. And these diamonds are the models for which we made cosmological simulations. So we have 10 simulations here. And using these simulations, so for these 10 simulations, we estimate the very weak evolution of shape of correlation functions. And then the dependence of this evolution on cosmological parameters is estimated from these multiple simulations. So if you want to know this systematic evolution at this cosmology, then you use these 4 simulations to interpolate the effect. And for this, and if you give the data whose true cosmological parameters is omega 0.26 and W minus 1, then this is the probability distribution you would get using the data. So this allows you to estimate the error bar. Okay. Okay. So I have explained by word, but this page has the same contents, but it summarizes in more accurate way. So let me just go through this page again. So we adopt flat wCDM model. So we are testing cosmological models. We are not testing all the models, but we are testing only this flat wCDM model, which Lambda CDM model belongs to. So Lambda CDM model, the standard model we have currently is a flat CDM model with W minus 1. And in this case, I allow W to vary, okay? And also omega matter is also pre-parameters. So we have observational samples, which I showed you before, in 7 different bins. And then you adopt cosmology, omega matter and W, and use the R of Z relation in that cosmology to convert the redshift of Sloan galaxies to co-moving distance, and then measure the correlation function in redshift space, and then normalize it. Okay? And this will give you the shape of correlation function in each redshift bins. And then you measure the difference in the shape of correlation function across the redshift bins. Okay? So delta Z. So this delta Z is basically the correlation function at one redshift minus the correlation function at other redshift, take into account the systematic evolution you expect for that cosmology. So I chose one cosmology, and I already know in my simulation that there will be this much of small evolution in the shape. So you take into account that expectation, and if there is anything more than this expectation, then you notice your cosmology adapted is wrong. So you go back to this first step. So this is the same thing. And we do this likelihood analysis to put constraint on these two parameters. So this is the result. So this pink area is the probability distribution of these two cosmological parameters allowed by our method, the pink. And if we compare our result with the others, the original supernova method has been evolving, and by 2018, this is the constraint they provided. And you can notice that the constraints from type 1a supernovae is basically parallel to our constraint. And later I'll show you why, but you can see our constraint is much tighter than theirs. So supernova constraint basically doesn't help at all. And the constraint from BAO, which used to be over here, okay, but about 8 years ago, the BAO constraint was over here, okay, and now suddenly BAO constraint went up to lower omega matter, and also the W much more positive than -1. So they now over here. There will be new constraints from this year, I guess. But the BAO constraint has some angle to our constraint. So if we combine BAO with ours, then we can reduce our error bar. And this gold contour line is the result of combining our result with BAO and supernova type 1a. And the result is omega matter of about 0.285 and W of -0.9. And what is important is the size of error bar. The error bar is only 0.023. So this is 4.2 sigma away from W -1. So this is very close to -1. But if you project this PDF to W plane, you will see this is basically incompatible with -1. One thing to notice is the fact that we didn't add CMB. And in cosmology community, most people try hard to ignore the fact that CMB is suggesting very negative W. And they are happy with the fact that it has a long tail, okay, crossing -1 over here. So everybody are happy with using this little tail overlapping with other constraints, and people tends to get W -1. But I think we really have to pay attention to the trouble with CMB constraint, which prefers W much more negative than -1. Okay. So in this study, we did not include CMB data. Okay. We just comparing the CMB constraint with the rest, which is basically from low redshift data. So low redshift universe is just suggesting W to be slightly larger than -1, whereas CMB is preferring value less than -1. Another thing I want to emphasize is that if W equals -1/3, which is over here, or larger, then universe is decelerating. And the fact that everybody is below -1/3, in particular our new constraints from Alcock-Paczynski test is absolutely away from -1/3, which means that universe is really accelerating. So it's not accelerating as fast as Lambda CDM predicts, but it is, we can clearly say that we are living in accelerating universe. There are a few comments I want to make before I reach the summary. One thing is the comparison of our method with respect to BAO method, because BAO is so popular and everybody is using it. It is my experience that we really need more than 1 million independent information to constrain W as accurate as possible and check if that is really consistent or inconsistent with -1. Okay, but I'm here. I'm trying to emphasize that you can never reach 1 million information if you use BAO. And if you observe all the galaxies out to Redshift 1, okay, and that is co-moving distance of about 2,300 megaparsec. And suppose you use all the galaxies out to Redshift 10, okay, then that is about co-moving distance of 6,600 megaparsec. You don't go much, even if you go out to Redshift 10. And then you measure BAO. And the BAO information is at 100 megaparsec. And the number of independent information in this data is only about 10,000 or 100,000. But BAO method I'm using is basically using the information at 10 megaparsec scale. And for given data, the same data is like 1,000 times larger data compared to when you use BAO. So you can easily go over 1 million information in your sample, even now. Okay. And another one is previously, the constraint on cosmological parameter from local measurement was so weak that you were forced to combine your data with CMB. And you always end up getting W -1 because your data from low redshift data tends to suggest W larger than -1, but CMB tends to suggest W less than -1. So if you combine it, you get -1 in the middle. But if you use Alcock-Paczynski test, now your constraint from local data is already tight enough that you don't need to combine your data with CMB. So that's one benefit. Another one is there is a parameter degeneracy in all these tests, as you saw in previous slide. So there's a degeneracy here, okay? And this degeneracy will be broken as your sample increases. And that is because at low redshift, the expansion history of the universe depends both on W and omega matter. So that's why there is a degeneracy over there. But as you go to high redshift, the expansion history is governed only by omega matter. It's independent of W. So this constraint will become more vertical, okay? So if you, as you increase your size of data and expand the redshift range, then your constraint at low redshift and constraint from high redshift will be combined to narrow down your parameter space. So there is that's what I mean by self-breakage of parameter degeneration. And that is much less achieved by BAO. Well, this is about the degeneration, but I'll skip this part. So let me summarize and conclude. So first, I'd like to say we confirm the accelerating universe by measuring W, definitely much smaller than -1/3. secondly, we constrained the flat wCDM cosmology using the extended version of Alcock-Paczynski test. And the standard shape we use is the Redshift-space correlation function. And then we measure W of minus 0.9, which is 4.2 sigma away from lambda, W equal minus 1. So there's no concordance anymore. And our measurement, the effective W, so the W we measure is basically the time average value of W between redshift about G equal 0.1 to about 0.7. So over this period, W can be increasing or decreasing. We don't know yet. We will measure the time factor later, but the W we measure here is basically the time average of W in this period. And the fact that we measure W effective to be greater than minus 1 means dark energy is not cosmological constant, but some dynamical field, like quintessence. Thank you.